Hi, this is Dr. Burks, and we're going to be jumping right into analytical chemistry, also just shortened to AChem. What is it? Well, I think it can be summed up like this. Analytical chemistry is about detection. It's about investigation. We design systems, methods, and techniques so that we can find answers to well-formulated questions. We can do it quickly, efficiently, and on budget, and we'll talk about all of these things. So being an analytical chemist is a mix between kind of being an engineer and also a chemist. So I love that part, and hopefully you will too. Let's jump right in and talk about the processes of chemical analysis. We are going to be doing a quick survey of some conceptual information in chapters 0 through 4. You're going to want to check out the detailed content schedule on our Canvas site to know which sections in those chapters that you're responsible for independent review. That's posted on our Canvas site, so make sure that you're checking it out. Okay, let's get started. In this class and in analytical chemistry overall, we are always interested in quantitative analysis. That's how much of something there is. But we're also going to want to know, of course, what it is. So qualitative analysis. So which one's more important? Well, they're equally important. You're going to want to know what something is, and you're probably going to want to know how much of it is there. Just think about some of the applications of analytical chemistry: environmental, clinical, forensic. It's important to know what it is, and it's critical too to know how much of it is present. Think about a diabetic. Do you have enough sugar? Do you have too much or not enough? Do you have enough insulin? Too much or not enough? These are things where we're also going to need to detect, okay, is insulin present? Is sucrose or glucose present? Is fructose present? And how much of all of those do we have? So we need to know both. Here's the 7 general steps for chemical analysis. First, you want to formulate a question. You need to focus. You're not just going to wander in the wilderness. Second, you want to select an analytical procedure. Or maybe you'll need to select 1, 2, or more. Depends on what your question is and what the context of the question is. You've always got to worry about sampling and sample preparation. Then we get to the analysis part: reporting, interpretation, and drawing conclusions. Note, we're 4 steps in before we actually get to the instrument, and we've got another 2 steps to go. So when we talk about analytical chemistry, we're talking about this entire process from start to finish, and we start by asking a question. Let's consider this scenario. You want to determine the caffeine content in a chocolate bar. So, what's your question? Okay, well, let's go with the easiest. How much caffeine is there in a chocolate bar? That seems pretty focused. We're trying to find the quantity of a known chemical. So we already have qualitative information. It's caffeine. Now we want quantitative information. We've got 1 sample, we've got 1 analyte, and we've got a very specific question. It seems good, but let's dig deeper. Now we're going to need to worry about an analytical procedure. This is where you've got to hit the literature, which is why you're going to the library on Wednesday. You've got to do the reading. There's no point in reinventing the wheel from scratch. Now, you might want to make improvements on the wheel, and we've certainly done that over time, but you don't need to sit around and start drawing circles. We've got that part covered. Now, you've got to know the literature, because you might have to actually come up with something completely new. How do you know it's new? You have to know what's existing or what was previous. And where do you start with a completely new design? Well, new designs actually tend to bridge off. Even if it's just a complete rejection of a concept, you start with someplace else, which is why you've got to know the literature. So first we jump in, we do our reading, we see the lay of the land. Then we decide, okay, can I use an existing technique? Can I use an existing technique and maybe modify it, or am I going to have to come up with something completely new? Next big question is sampling. You've got to get a representative sample of your material. Let's face it, you're not going to consume the entire sample. In fact, it would be really a bad idea to do that. And in some situations like forensic work, environmental work, and clinical work, it could actually be illegal to consume the entire sample. You've got to be able to have enough for secondary, tertiary, maybe even quaternary checks. We're talking double, triple, quadruple checks. Remember, the more important the context, the more checks, triple checks, and bajillion checks that you're going to do. Now that's even different than doing replicates of the same sample. So we've got to get a nice representative sample. A poorly chosen sample, or one that was not handled correctly, wasn't stored at the right temperature, wasn't treated in the right way, that means you're going to get bad results. And by bad, we mean meaningless. If you don't control every step of the procedure, your data is questionable. Questionable data is bad or meaningless data. Now here's where broad statements really come back to bite us. If you've said something way in the beginning, like, oh, let's find out caffeine in chocolate, we thought that was pretty specific, one type of analyte in one thing. However, turns out that's actually pretty broad, and that might require some pretty extensive sampling. We'll go through that in a little bit more detail. Think about a pure chocolate bar. Now, if you're going with the plain old Hershey bar that you might use to make s'mores, that's fairly homogeneous, meaning a consistent composition. It's a safe assumption that you could, say, punch out a hole anywhere or take any of the Hershey squares, and that's pretty consistent or a representative sample of the entire bar. You wouldn't need to consume the entire bar. Remember, you wouldn't even want to. You could probably just take a small little piece and it would be representative of the whole thing. If it's representative of the whole thing, then the percentage of caffeine in that piece would represent for the entire bar. That sounds great. Now, however, remember, our general question was, how much caffeine is there in a chocolate bar? Problem is, we didn't specify what kind of chocolate bar. Is it actually a homogeneous chocolate bar? Or is it a heterogeneous chocolate bar? Maybe we like chocolate with macadamia nuts. You've got all this nuts in there. Maybe it's even a Snickers, which is even a worse case scenario because that's got all kinds of non-chocolate stuff dispersed in between with this weird chocolate coating. Who knows what's going on? That's a heterogeneous material. That is an entirely different sampling situation. Instead of being able to take one representative piece like in a Hershey bar, if you had one of these chocolate nut bars or like a Twix or a Snickers or anything like that, you might actually have to take 5 or 6 samples from across the bar to get a representative quote-unquote sample. So those are two very different scenarios. So what do we mean by chocolate? We've got to be very specific, because the more specific we are in our question, the easier our sampling is. Remember, by easier, we don't maybe even mean less steps. Maybe we are going to want to deal with the chocolate macadamia nut bar. But we've got to have a clear goal so that we can design a sampling protocol to meet that goal and not waste any time on extraneous steps. If we're focused on a homogeneous bar, we don't need to worry about a heterogeneous sampling situation, and vice versa. Then we've got to worry about sample preparation. So we've got a representative sample. Now that we've sorted that out, how are we going to convert that into an actual thing we would say inject in a machine? Here's where the sample prep, from my professional experience, can take way longer than the instrument time. Think about chocolate. It's a lot of stuff. It's got sugars, fats, water-soluble stuff like sugar, and heck, caffeine's water-soluble. Drink it in your coffee and your tea and your soda. That's a lot of different stuff. Fats aren't solubles in water, so stuff's going to start separating it out. Right now it's a solid. What are we going to do with it? You can see the steps starting to add up. We're going to need to convert our representative sample into a form that's suitable for analysis. This typically means we're going to have to dissolve it, separate it, maybe even concentrate it down. Some other samples might need to be volatilized into the gas phase. I mean, there's a lot of options. Let's focus on our chocolate. Chocolate's one of those weird things. It's very temperature sensitive. We know that. You can have hot chocolate, you can have chocolate milk, you can have chocolate bars. If it's a hot day and you leave your bar out, it'll be chocolate soup. For this situation, we're probably actually going to maybe even freeze dry the chocolate or put it in the freezer. Get it really cold so it's a nice solid. Then we're going to get out our mortar and pestle and we are going to crush that into a nice fine powder. Why is that? We're going to want that surface area. Remember, we want to extract out the caffeine from our sample. And if we want to dissolve it, it would be easier to do if it's a nice fine powder, evenly distributed, right? Nice homogeneous powder. So that's probably what we're going to go for. Now after that, that's where we're going to have to separate the caffeine and your water solubles from things that are fat solubles. So we're going to do a solvent extraction. This should sound familiar from organic. So we're going to take our old friend pet ether. We're going to throw some chocolate into it. This does not sound good in any way. And that's going to get a nice suspension going. Now, the stuff that's soluble in pet ether are going to be your fats and your oils. That's the stuff you actually don't want. You want all the solids because your caffeine, that's going to go down into your solids because it's not fat soluble. Caffeine is water soluble. It's going to stick in with the solids. You're going to decant off then your pet ether, and you're going to be left with what's called your defatted residue. So all the delicious fats that make chocolate, tasty chocolate, are gone, and you've got this defatted residue. But that's actually good. We're going to keep that because that's where our caffeine is. Now, that's easy peasy because what we're going to do then is make, well, watery hot chocolate. We're going to take the defatted residue, put it in boiling water. Now remember, that caffeine, sure, there'll be some other solids in there. Remember, we don't care about those. We just want the water soluble bits. Caffeine's very water soluble. So we're going to get those out. We're going to spin it down. We're going to keep the supernatant this time because that's your water soluble stuff. The caffeine will be in there. We're going to set aside the insoluble chocolate residue. Okay, put that to the side. Then our water soluble fraction, we're going to filter that, little micron syringe filter, collect that, and now that heavily filtered, nice water soluble bit is what we're going to put into our chromatograph. We're probably going to use high performance liquid chromatography here, HPLC, which we'll learn about a lot in this class and you'll be doing in lab. Then we're going to do another thing. Yes, even more! Solid phase extraction. That's a little bit close up of the step we just did. So remember that little filter, the little spin filter? This is kind of a really blown up version of that. It's another filtering phase because again, you don't want any of that solid matter to somehow get onto your column. It'll totally gunk up all the lines. Then it will change the pressure. Remember, you're going to be using a high performance instrument. It's going to be under tremendous pressure. So we want all the solids out of there. We want all the stuff that's not water soluble. So any sneaky stuff that might have gotten through is going to get out when we do our solid phase extraction. Then that bit is what we inject in. So this is kind of a blown up right here, that little micrometer filter. It's kind of a blow up of that with your solid phase extraction syringe. So we do all of that and we are going to inject it right there in the top into our HPLC system. We're going to be using this hydrocarbon bonded to silica packed in there. And then it's going to be a simple UV detection because caffeine absorbs at about 266 to 275 depending on what solvent it is, so about 272 in aqueous solvents. So we can certainly detect that in the UV. Now we're going to see. This is kind of on the right here is kind of a blown up cartoon version of what's going on. You probably did column chromatography organic, or TLC, thin layer chromatography. So this should look really familiar. So peaks are going to start to separate, and we notice that we've got a caffeine, and then we've got theobromine. It's going to turn out that theobromine and caffeine are very structurally similar, and so they are both soluble in the same solvent. So even though we did all that sample prep, turns out we still got two things. That's why we've got to do this chromatography, the separation technique. They separate out really well, and so we're actually going to be able to tell them apart and quantitate them, because you would make up a standard curve with standards of each of these, or really you just want to know which one elutes when, so that you can focus on the one that you want, which for us is caffeine. So when it elutes, it's a big difference between the two. Remember, if you didn't do the chromatography, you would just get this giant peak. Now here's the deal. You've got way more theobromine in your chocolate than your caffeine. This is why it's so dangerous for the pups. Theobromine is toxic for dogs, and there's a heck of a lot of it in chocolate. Caffeine's no problem in comparison, but look how much of the theobromine there is. If we hadn't done the separation, we would really greatly overestimate how much caffeine it is. Remember, if we hadn't done the separation, these things would be coming out on top of each other. If we just use, say, UV spectroscopy, which you've done in labs for a couple years now, you would have gotten a giant peak, because look at them, they absorb very close together. They must in the UV at 254. You're going to get this giant peak, which would have given you a completely incorrect concentration. So that's why it's key that you've got to separate them out. Literature search would have revealed that to us, right? And if we look at the structure, again, look how similar they are. The only difference between the two is the methyl substituent in that amine group. Secondary amine goes to a tertiary amine. That's the difference between the theobromine and the caffeine. That one methyl group makes all the difference. So we construct our standard curve. You're going to take different concentrations, and you're going to construct these curves. So you remember, you did your UV analysis at 254. We've got two very different curves here, right? You've got your caffeine center curve, and you've got your theobromine center curve. So we've taken known standards of each one in parts per million. That's our units for this particular example. And we've got a nice center curve, and then we plot our unknown absorbance value, and we can figure out, okay, what is its concentration. Now notice here that we've got a really steep line for theobromine, and the caffeine line is much flatter. Not flat, but flatter than theobromine. Well, what that means, and you'll learn this in detail when we get into chapter 5, is that theobromine is absorbing more strongly at 254. 254 is much closer to theobromine's absorbance maximum. Caffeine's absorbance maximum, remember I said, was about 10 to 15 nanometers higher. That's why it's a bit flatter. So we're also going to want to make sure that if we're really looking for caffeine, we'd be better served using that higher wavelength. We'll find out why this might have been limited as we get into our spectroscopy instruments and detectors. Now, if you look at this graph, another thing you might notice is you've got 1, 2, 3, 4 dots per analyte. Did they do any replicates here? There aren't any error bars, and there really should be. If you're doing analysis, you're absolutely going to rinse and repeat so you can have replicates so that you can look at statistical analysis. And absolutely, chapter 4, again, check to see which parts you're responsible for your independent review. You're going to want to know what's your error for each concentration. It turns out that oftentimes At low concentrations, things struggle. It's hard to find really small quantities of stuff. And the error bars tend to decrease as we increase concentration. And again, you'll learn over this semester why that's true. But this Beer's law plot, which is what it is, should look really familiar to you. And we'll be using this quite a bit in lab, and we'll be talking about it in detail in lecture. Even though HPLC was used, the detector for HPLC is a UV vis spectrophotometer. So, of course, we can use Beer's law on multiple analytes that are separated now by time and still construct a Beer's law plot. It's pretty cool. Now, this is all fine and good, but somebody is going to want you to communicate your results. You're the scientific expert, but you've got to report and interpret your findings. And you've got to do that in a clear, concise way. You want to communicate what the results are, qualitatively and quantitatively, and interpret them for the person that is the person who's going to receive the report. So, if you're writing the report to, say, a medical doctor, but you're a toxicologist or a pathologist, you actually are going to need to write it for them. They might be wanting to make a diagnosis. How can your report help them? When I worked in a crime lab, I was writing reports for attorneys, law enforcement, very different set of people than other scientists. How can I be technically correct, but also jargon-free? You want to make sure your reports are, again, technically correct, jargon-free if that's appropriate to your audience, and get to the point quickly. In the words of journalists, don't bury the lead. If you've got an important finding, you want to lead with that first. And again, always, always, always make sure the report is appropriate for its intended audience. Oftentimes, you'll be writing a couple of different versions for the same set of analysis. So you might be writing one thing to another expert to maybe have them review your work, or for a journal article. So that would be a very different communication than, say, one that you would release to, say, your local representative who wants to know your research because he's voted to increase NSF funding. Well, if they're not a scientist, it's a completely different report. So make sure it hits the intended audience, that it's technically correct, and it's well communicated. It's always the goal. There is really great data out there, and it has really interesting meanings. But if it's not communicated well, all of that great science and great work gets lost in confusion. Now, drawing conclusions is critical. While data itself, you could say, oh, it's hard numbers, that might be true. But think about this. The design of the question, picking which question, that's your choice. That's a bit of an art. You had to subjectively decide what was important. So the question is going to influence your experiment. So you've got some subjective things coming in right away. Then you look at the data, right? And oh, and by the way, you made a decision on what kind of analytical technique, what kind of sampling protocol you were going to do. These are all subjective. Now, they're subjective, but they should be based on a high degree of technical skill, conceptual knowledge, and professional experience. But they're still subjective decisions. You're still deciding to do one thing to the exclusion of something else. You've got to be able to back that up. But it's still a subjective decision. Same thing goes with drawing conclusions. Why is this important? What does it mean? You've got to make a choice based on, again, your technical skills, high degree of competency in your field, and hopefully years of professional experience. Based on your experience and your knowledge, you're going to be asked to make decisions. It might be a decision like, is this appropriate for the product we're making, or do we need to shut down this line because there's a problem? That's a subjective decision, and you're going to make it based on the best data available to you, again, your expertise and experience. There's a lot of choices that we have to make as scientists, medical researchers, forensic scientists, environmental. You might be working in energy or climate change. It should all be data driven, but you're still going to have to make human decisions because you are a human being doing science. It can seem daunting, but again, you're going to have high levels of technical skill, years of studying and working on a particular area, and lots of professional experience. And that starts definitely for analytical. You're going to continue that in this class, right? This is to get you to the point where you can be more confident that your decisions are grounded in data, they are grounded in a good conceptual foundation, and that you can put forward something that makes sense. Now again, the more clearly a report is written, the less likely it will be misinterpreted by those that use it. Remember, if you hand off a report, whether it's writing, whether it is an oral report, whether it's a poster, once it's out there, right, it's up to the other person to interpret it. What if they misinterpret it? Well, is that because you didn't communicate clearly, or we didn't communicate clearly, or is it because they really are just confused? So the clearer we can be, the more time we can spend laying a good groundwork and then moving into more complicated topics, the better. If you've given a poster or helped a professor write a paper, or you've presented at, say, Source or Lucian or at one of our ACS regional or national meetings, you know, for a poster included, that you start with background, right? Why is this important? What's the problem I'm looking at? Why is it important? What's the method I use, right? You're starting with laying a foundation, and then you're explaining very succinctly, clearly, using data, using visuals, right, to lead them to, hey, here's my conclusion or my interpretation based on all of this information. We want to make it very clear so that there's little teeny bit of room, if not no room, for misinterpretation. This comes with practice. Practice, practice, practice. And we'll get that in lab definitely. It'll be a nice parallel for this class. You'll get experience working on your technical writing in addition to developing your technical skills. Now, looking ahead, make sure you read the syllabus carefully if you haven't already. There's also an online extra credit syllabus quiz on Canvas. Hey, when's that due, by the way? You should take a look. Make sure that you read the detailed content schedule. It's right on our Canvas front page as a PDF. For Wednesday's 9 a.m. class, just as is posted on, again, the front page at Canvas, make sure you meet sharply at 9 a.m. in Mundi Library 115 to get a guest lecture and a nice help from our librarian, Miss Nicole Oglesby. Please be on time and engaged, as I know you will be, and remember, attendance will be taken. For Wednesday's 2 p.m. lab, we will be remember, I won't be there. You'll be meeting Dr. Lizette Curry in JBW North 102. She is going to be leading you through an excellent safety experience. It is safety first. Just like I say in the Canvas announcement, it is absolutely our #1 priority. All 6 of us. Okay? We have got to keep each other safe, and we've got to keep ourselves safe. Okay? So please be there. I will see you all on Friday. Have a great first week.